Welcome to Lecture 12, Partial Fraction Decomposition. This is a lecture that you'll find very useful not just in this class but in later math classes, assuming that you take beyond the calculus sequence. Okay, so as an overview, let me ask the question, how do I evaluate an integral like this one? This is a quotient of two polynomials, and we have a quotient theorem for derivatives, but we don't have one for an integral. So it seems like something we should be able to do, but we haven't learned any technique that's going to work. But what if I told you that you could write this fraction, you could break it up into two fractions and write it like this. So this fraction, you can check, actually equals this fraction plus that fraction. Now once I've given you this information, now this becomes quite doable because I can write this as 3/4, the integral of dx over x plus 3. And this second one is plus 1/4 integral of dx over x minus 3. And now these are just natural log. I mean, if you want to be picky about this, you can do this one and you can say let u equal x plus 3, and with this one you could say let u equal x minus 3. In both of these cases you're going to get du equals dx. Over here du equals dx. That's because the coefficient of x is 1. And so anyways, when you do this, I'm going to skip that step and I'm just going to say that these integrals, this one is equal to 3/4 natural log of x plus 3, and this next one of 1/4 natural log of absolute value x minus 3, and of course I need a plus c. So once you know how to break up this into this fraction, we call this a rational function, into we call these partial fractions, then the integral becomes quite easy. The technique is called partial fraction decomposition, and let me give you a definition. A rational function is a quotient, f of x over g of x, where f and g are polynomials, and g is not 0. So this triple equals mean it's not the 0 function. It's okay if it has zeros. It might have a few roots. So this doesn't have to be defined everywhere. It's defined at all points where g does not have a root. The only restriction is that g can't be the 0 function, otherwise this obviously is not defined. So a rational function is proper if the degree of the top is less than the degree of the bottom. Otherwise it is improper. So if it's improper, we could continue like long division and factor it more. So this function right here is proper, and this one here is improper. So why this works is, here's a theorem. I mean, this is something that you know just from basic high school algebra. Any polynomial with real coefficients, even with complex coefficients, can be factored uniquely into products of linear and irreducible quadratic factors. Basically, you know that any degree n polynomial, so if f of x, so if f of x is a x to the n plus, a n x to the n plus a n plus 1, what am I doing? A n minus 1, a n, so plus a 1x plus, so suppose we have some degree n polynomial, we know it's a fundamental theorem of algebra that f has exactly n roots in the complex numbers. There could, well, counting multiplicities. So what that means is we can factor f of x. So if we wanted to, we could factor f of x as x minus root 1, x minus root 2, r2, x minus root, etc., all the way up to x minus rn. So if we do that, some of these are going to be real. All the real roots come in, are represented by linear terms, and then the And then some of these might be complex roots. It could be like x plus I and x minus I. And so those, so some of these later might be complex roots. We know those come in complex conjugate pairs. So what this is saying is any product, any polynomial can be factored over the, here's the key, the real numbers into products of linear factors. These are corresponding to real roots, and irreducible quadratic factors, these correspond to complex. Let's try complex conjugate roots. For example, here's a polynomial. We can factor it. This thing has 4 roots, has x equals -2, x equals 1, and x equals plus or minus I. And the real roots, you can see -2, this term, +1, and then the complex roots appear in this. This is an irreducible quadratic term. Okay, so here's an example similar to the one that I showed you on the first slide. On the first slide, I showed you how to integrate something once we have split up this fraction, but I haven't showed you how to actually split it up. So the idea, as you've seen before, is that for each linear factor that we have, something like this, we would like to split up this fraction as a sum of fractions like this. In other words, we want to turn this integral into a over x plus 7 plus b over x plus 1. Now that's something we could do. So all we have to do now is figure out how to write this like that. Okay, so let's do that. So basically we want to figure out how to write this fraction, x squared plus 8x plus 7, as a over x plus 7 plus b over x plus 1. Now I left a little room because how to do this is, well, we want to make each of these terms, we want to solve for a and b, let's make each of these terms have the same denominator as this. So I'm going to multiply top and bottom of this fraction by x plus 1, and top and bottom of this fraction by x plus 7. Now why does that help? Well, oh, I forgot my fraction. So now the bottom of this fraction is x plus 7, x plus 1, and notice that is the same as this. So if we want these two things to be equal, well, their bottoms are equal, so their tops better be equal. So the top of this fraction, I'm going to write it as something times x plus something else. And the question is, what are those somethings? So how many x's do we have here? So we have a times x and we have b times x. So we have a plus b x's right here. And how many? What's our constant term? Our constant term is a times 1 plus b times 7. So this is a plus 7b. And now all we have to do is this fraction has to equal that fraction. Their denominators are the same, so the numerators have to be the same. So we have to set, so this is just a linear function. It's a degree 1 polynomial, and so is this. Well, let me write this as 0x plus 1. And now you can see 0x plus 1 has to equal a plus bx plus a plus 7b. In other words, 0 has to equal a plus b, and 1 has to equal a plus 7b. In other words, we have a system of equations. We need to solve, well, let me write it first as 0x plus 1 equals a plus b x plus a plus 7b. So the coefficient of x better be equal to the coefficient of x on the right-hand side. So these must be equal. And the constant term on the left-hand side must be equal to the constant term on the right-hand side. So those must be equal. This gives us a system of equations. 0 equals a plus b, and 1 equals a plus 7b. So let's solve this. This first equation tells us that a equals negative b. So if we plug that in into here, plug our negative b in for here, we get 1 equals negative 6b. So 1 equals negative 6b. So our solution, or our answer is, we get b is, I'm sorry, did I say negative 6b? Positive 6b. Negative b plus 7b. So b is 1/6, and a has to equal negative 1/6. It's a is negative b. So now our integral of dx over x squared plus 8x plus 7 is really equal to this thing here. I'll write this as two integrals. The first one being the integral of negative, let me make that a pen, negative 1/6 over x plus 7 dx plus integral of positive 1/6 x plus 1 dx. So if I wanted to, I could pull out the constants. So negative 1/6 integral of dx over x plus 7 plus positive 1/6 integral of dx over x plus 1. And if I wanted to, I could do u substitution. Let u equal x plus 7, but we would just get du equals dx. And similarly, we could, same thing here, let u equal x plus 1, and we would get du equals dx. So I'm going to, because that works because these x's are monic, the coefficient is 1, we don't really have to do u substitution. I can just write this as negative 1, as negative 1/6 natural log of x plus 7, that's the value of x plus 7, plus 1/6 natural log of x plus 1 plus c. And that is our answer. Okay, so a slightly harder case is we have repeated linear factors in the denominator. So here we don't just have an x, but we have an x squared. So we have two of the same, this is like x, a linear factor, x minus 0. So we have two of these. So the same goal, we want to split this up into fractions, but now the fractions are a little more complicated. So the strategy here is for each fraction, each repeated linear factor, the partial fraction decomposition contains a partial fraction, one for each power. In other words, for here, we want to write this as well, let's see. So our repeated term is, so we have x minus 0 to the second. So for here, r equals 2. So I want to write this as a over x plus, instead of a1 and a2, I'm just going to use a and b over x squared. Notice that this term is just that. My ax plus b is just x, and my ax plus b squared is just x squared. So basically, I just have so normally if this were plain old x, you would just have this, but now you have to have an extra term because it's repeated. And then finally I need a term for c over x minus 2. Again, so the only difference here is because this is repeated, I gotta have two terms like this. Oh, and let me stick a dx on the end here. Okay, so let's do this. As before, we need to write this fraction, x plus 1 over x squared x minus 2. We have to write this as a over x, I'm going to leave a little room, plus b over x squared. Again, I'm going to leave a little room. Oh, I said I would leave room and I didn't. And then let's go back to my pen. Plus c over x minus 2. Okay, so to do this, I need to make the denominators the same, so I have to multiply the bottom here by x times x minus 2. I got to multiply the top as well, x times x minus 2. Now this bottom is missing, well, it's not quite that, it's missing an x minus 2, x minus 2. And then this last one is missing an x squared and an x squared. Okay, so as before, we have to figure out what a, b, and c are. So this right-hand side now, I'm going to write as a big fraction. On the bottom, of course, is going to be x squared times x minus 2. And on the top, what are we going to have? So we have, it's going to be a polynomial in x. We're going to have at most x squared. So we're going to have an x squared term, we're going to have an x term, and we're going to have a constant term. So how many x squared, so let me say it's going to be something times x squared plus something times x plus, so it's going to be something times x squared plus something times x plus something. So how many x squareds do we have? I only see one. I see a times x squared. So that's going to be ax squared. Is that right? Yeah. So how many x's do I have? I have a times x times negative 2. So that's a negative, oh, hold on. I forgot an x squared. Out here, there's an x squared. I almost missed that. So a plus c x squared. Okay. Now for how many x's do I have? I have, again, a times x times negative 2. So that is negative 2a. And then I also have b times x. So I have plus b. And then what constants do I have? I have a times negative 2, and I have b times negative 2. So I have negative 2a minus 2b, right? Okay. So that whole thing has to equal the left-hand side of the equation, which x squared times x minus 2 is on bottom, and the top is going to be, well, let's see, I have 0 x squared plus x plus 1. So I have 0x squared plus 1x plus 1. Those are both 1s. So now I have a system of three equations. I have, so let's see. So the x squared coefficient, tells me that 0, that is this 0, has to equal a plus c equals a plus c. The x coefficient, 1x, so the x coefficient tells me that 1 has to equal negative 2a plus b. So that's 1 has to equal negative 2a plus b. Must be a b. And then the constant term, this coefficient of 1, has to equal negative 2a minus 2b. So 1 equals, let's write it, this as 2, or negative 2 times a plus b. So this is something you can solve rather easily. I'll just tell you what it is. It is, yeah, this is just an algebra problem. You learned how to do this in 8th or 9th grade. So I'm just going to say solve. On your homework, you are welcome to use a computer for this, like Wolfram Alpha or something like that, if it's just algebra. But know that this is something that you need to know how to do. It's fair game for me to give you something that involves a 3x3 system on an exam. Okay, so once you solve this, you get that, I believe you will get that a equals negative 3/4. That means, so, since a and c are negatives of each other, that means c will equal positive 3/4, and then b equals, let's see, so b is negative 2a, so that's 1.5. So b is, no, I'm sorry, b is 1 plus 2a, so 1 plus negative 1.5, so that is negative 1/2. Okay, so now that we have that, the next step is to take those numbers. Once we plug those into here, now we have 3 integrals that we can do. So let me summarize. So we've written this as, oh, let's switch back to black. We've written this as a over x dx plus integral of b over x squared dx plus integral of c over x minus 2 dx, and we've determined that a equals negative 3/4, b equals negative 1/2, and c equals positive 3/4. So these integrals become negative 3/4 integral of dx over x plus, oh, let me do a minus. Let me subtract 1/2 integral of dx over x squared. And let me add 3/4 dx over x minus 2. So now this is easy. This first term is negative 3/4, natural log of absolute value of x. The second term, let's remind ourselves what this is. So this is the integral of x to the negative 2 dx, which is equal to negative 2x to the negative 3. Oh no, that's not right. I'm sorry. I did the wrong one. That's, what is that? That is x to the negative 3 over negative 3. I don't have to worry about a constant. I'll add that in. Well, let's put the constant there for completeness, or maybe it's a slight OCD thing on my part. So this is minus 1/2 times x to the negative 3 over negative 3 plus 3/4 natural log of x minus 2 plus c. So our final answer is negative 3/4 natural log of x minus, so that's a plus, x, let me write this as 1 over 6x cubed plus 3/4 natural log of x minus 2 plus c, and there's our answer. Would you ever have guessed that the integral of this innocent leaking fraction is going to look something like this, involving natural logs and 1 over x to the negative 3's? Okay. So case 3, let's get a little more complicated yet. Now we have distinct irreducible quadratic factors. So here's an example of this. And the strategy is to, for each one of these factors, in this case, here's our factor, we need a term that looks like this. And notice this is a distinct irreducible factor. It's distinct because it only occurs once. This occurs twice, but we don't care about that. This is not irreducible, it's not, and we know how to deal with that. So to summarize, what this is saying is that in this case, we want to split up this fraction as a plus, sorry, not a plus, but ax. So we want ax plus b over my irreducible quadratic factor, x squared plus 1 in this case, plus, and so this takes care of that term, and then we know how to take care of that term. We just did that. That would be, we have a c times x minus 1 plus a d over x minus 1 quantity squared dx. Okay, so to do this, as we've done before, we are going to write our, that shouldn't be an a, that should be a 4. We're going to write our original fraction, 4 minus 2x over x squared plus 1, x minus 1 squared. And this thing we have to write as ax plus b over x squared plus 1, let's leave a little room, plus c over x minus 1, let's leave a little more room, plus d over x minus 1 quantity squared. So I got to rationalize this denominator. So this first term I need to multiply. So again, I want each of these denominators to be equal to that. So this first term I have to multiply by x minus 1 squared. Just to make things easier, I'm going to multiply out x minus 1 squared on the top. So this is going to be x squared minus 2x plus 1. Now over here I need to multiply by x, I'm missing an x squared plus 1 times x minus 1. Well, maybe at some point. Okay, so what is, let's multiply this out. On the top this is x cubed minus x squared plus x and minus 1. And then here I need to multiply by x squared plus 1 over x squared plus 1. Okay, so now to summarize, on the denominator, we can combine these into one fraction. That denominator equals this one. The top, this numerator is a degree 3 polynomial, and this thing here is, well, it's not a degree 3 polynomial, but we can write it as one. So we could write it as 0x cubed plus 0x squared plus or minus 2x plus 4 over x squared plus 1, x minus 1 quantity squared. Now the right-hand side, we have a whole big mess over this. So we have x squared plus 1, x minus 1 squared, and then whatever the top is. So let's see if we can figure out what this is. Okay, so what is this? So we have some number of x cubed. How many do we have? We have, see, we have an a here, an ax times x. No, wait. Let's put parentheses here. I'll need that. Yeah, that's good. Okay, so how many x cubes do we have? We have an a x times x squared. There's an x cubed, coefficient a, and we also have a c times x cubed. So we have a plus c x cubed. Okay, now how many x squareds do we have? We're gonna have a few of these. We have a b times x squared here. We have, I'm just gonna write them down as we get them, otherwise I'll lose track. So we have just in this fraction we have we have a times negative 2. So ax times negative 2x, and we have a b times x squared. So that's going to be negative 2a plus b. I hope I have enough room for this. What about this term? We have c times negative x squared, so that's minus c. And now this is, we have plus d times x squared, so we have plus d. Okay, great. So we have everything there. So next we have some number of x's. I should have given myself more room out here. So how many x's do we have? We have, again, I'm just going to write them down as they come up. We have a times 1. So we have a. We have a b times negative 2. So minus 2b. We have a c times 1. So we have plus c. And we don't have anything over here. So I'm going to end that, and I'm going to put x. I hope I have enough room for my constant term. So what are my constant terms over here? So we have, a is not going to have any constant term because there's an x in front of it, but we have a b times 1, so we have a b. We have a c times negative 1, so we have a b, we have a minus c, and then we have, minus c, and then we have a d times 1, so we have plus d. Okay, so to summarize, it looks more complicated, but we're doing the same thing. Once we know, if we know the right type of our partial fraction decomposition, then here, no matter how messy it is, it's just algebra. It's the same. It's the same process. So now we have 0, 0, negative 2, and 4 that we must set equal to that, that, and that. So we have a system of 0 equals a plus c. We have 0 equals negative, so this 0 equals that 0. Now this 0 has to equal that creature. Negative 2a plus b minus c plus d. Next, this negative 2 has to equal that, so negative 2 equals a minus 2b plus c. And finally, we have 4 has to equal that, so 4 equals b minus c plus d. Okay, so this, I'm just going to tell you, this is, you could do this by hand. On the homework, I encourage you to use a computer to do this. I mean, obviously you can do this by hand, but don't waste your time. The point of this problem is not solving this 4x4 system. The point of the problem is getting here, getting the right system, and then once you have that, being able to do the integral. Okay, so I'll just tell you that the solution to this is a equals 2, b equals 1, c equals -2. Is that, yeah, and d equals 1. So this is the information that we're going to need, and we want to plug that up into there. Okay, so let me summarize. So we have written this now as the integral of ax plus b over x squared plus 1 dx plus, I'm gonna factor out the c, why not, over, what was there? There was a dx over, that's right, x minus 1 plus d times the integral of dx over, it was x minus 1 quantity squared. And we had that, right, a was equal to 2, b was equal to 1, c was equal to -2, and d was equal to 1. Okay, so let me just plug this back in. And I'm going to do one more thing. This thing I can break that into two integrals. I can write that as a times x over x squared plus 1 dx plus b times dx over x squared plus 1. So that's what I'm going to do. So we have now we have 4 integrals. So our original integral is 2 times the integral of x over x squared plus 1 dx. The second one is plus 1, so integral of dx over x squared plus 1. The next one is minus 2, so minus 2 times dx over x minus 1. And finally we have plus 1 times dx over x minus 1 quantity squared. Now, I think now would be a good time to pause the video, and as practice, you'll have this on a midterm coming up soon, as practice, make sure you can actually solve all 4 of these integrals. You've recently learned how to do them, so give that a shot. Okay, so, and I'll tell you the answer. I won't do them, just out of interest of time, but I'll let you pause the video and do that now. Okay, welcome back. If you did that, I'll write the answers to this. This first integral is a natural log of x squared plus 1. And now what technique would you have done for that? Would have been u substitution. Let u equal x squared plus 1, right? This next integral is inverse tangent of x. Now that's just one you're supposed to know. When you see 1 over x squared plus 1, you know that's inverse tangent. This next one is 2 natural log of x minus 1, absolute value of x minus 1, and the last one would be, so this, also a u substitution. Let u equal x minus 1. And so this last one is going to be minus 1, let's go back to a pen, minus 1 over x minus 1, and finally plus c. Okay, there is our final answer. And once again, you probably would not have guessed a few days ago that an integral like this would ever have a solution involving a natural log, x squared, an inverse tangent, and a 1 over x minus 1 all put together, but hey, it does. Okay, so the last case is when we have repeated irreducible quadratic factors. So far we've dealt with the case when we have distinct linear factors, distinct irreducible quadratic factors, repeated linear factors, and finally when we have repeated irreducible quadratic factors. That's the last case we haven't done. Once you have those, you can do any partial fraction decomposition because you just treat each type of term separately. So the strategy here is for each, it's the same as the last one. For each irreducible factor, ax squared plus bx plus c to the r. So each one like this, the partial fraction decomposition contains a sum of r terms, just like what we had before. It's just now, instead of this being a linear term, it's a quadratic term. In other words, for this one here, I'm going to write this as, let's see, so now our ax plus squared plus bx plus c, that's just equal to x squared plus 2, and r equals 2. So this is just the integral of, let's see, so we need a ax plus b over x squared plus 2, but we also need another one for x squared plus 2 squared. So we need a cx plus d dx. So I'll get you started on this. I'm not going to finish though. Oh, maybe I will. We'll see what time we have. So as before, we start with this fraction on the left hand side, x squared plus x plus 2. This is the thing that we need to break up. And we have to write this, so that we have to write as this plus that. So we write this as x squared plus 2 on the bottom, and ax plus b, and let's leave a little room, plus x squared plus 2 squared times cx plus d. Okay, so now here we have to multiply by x squared plus 2, top and bottom, x squared plus 2. Let's put in parentheses to make sure that we don't do anything wrong. And then on this right term, looks like we have it. So now we have, on the left-hand side, so we have x squared plus 2, quantity squared in the denominator. And on the right-hand side, well, we of course have that in the denominator, x squared plus 2 quantity squared in the numerator. Let's see what we have. So we are going to have, the highest term we're going to have is going to be an x cubed, x times x squared. So we're going to have some number of x. I don't think this is going to be daunting in terms of as many terms as we had before. So this is x cubed, or sorry, we have, how many x cubes do we have? We have a of them. So we have ax cubed. How many x squareds do we have? So we have some number of x squareds. So we're going to have, let's see, we have an a time, wait, do we really only have, yeah, we only have, all we have is the b times a. So we have, I guess I can let me erase this. I was going to put a parenthesis. Come on. Let's go back to my pen. It won't let me do that. Okay, fine. So I'll just turn this into a b, x squared, plus, what's my linear term? I have ax times 2, so I have 2a. I also have a b times 2, so I have plus, no, that's a constant term. That's the only linear term I have here, but I have one here. So plus c x. And then what's my linear term, or my constant term? I have a b times 2, so I have a 2b plus a d out here, so plus a d. And out here I have 0x cubed plus 1x squared plus 1x plus 2. So this gives me a system of 0 equals a. Again, that's 0 equals a. 1 equals b. This is easier than the last one. 1 equals b. 1 equals 2a plus c. 1 equals 2a plus c. And the last one is 2 equals 2b plus d. 2 equals 2b plus d. So a is 0, we can get rid of that, we can get rid of that. B is equal to, so this tells us that a equals 0, b equals 1, c now equals 1, and d is 2 minus 2 times 2 minus 2. Oh, d is equal to 0 as well. So that's interesting. So this whole fraction turns into 1 over x squared plus 2 plus 1 over x squared plus 2 quantity squared. Okay, so that's nice. This integral we've determined equals integral of 1, so dx over x squared plus 2 plus 1 times x over x squared plus 2 squared dx. So this first integral is equal, this is just an inverse tangent one, so this is inverse tangent of x over root 2 all over root 2. I'll let you carry out the details if you so wish. And this one, we do u substitution, so we let u equal x squared plus 2, so we get du equals 2x dx, and so I look at this, and I'm going to do this slightly different from how I did the previous u substitution. I look at this and I say x dx is what we want, so I'm going to write this as x dx equals 1/2 du, and that is what we want to substitute in for there. So this integral now becomes, let's move that over here, and so our integral now is, well, let's see, what is this? It is 1/2 times 1 over u squared times du. So this is 1/2. I still like to write this to this day as u to the negative 2 du. So now this is 1/2 u to the negative 1 over negative 1, which is, let's be careful here, this is negative 1 over 2u, which is negative 1 over 2 x squared plus 2. So I'm omitting the plus c because I'll add that in at the end. So there's the answer to our first piece. There's the answer to our second piece, and so our answer to the integral is just the sum of these. So is inverse tangent of x over root 2 all over root 2 minus 1, well, let's make it undecisive as to how to write the fraction. Let's keep it like we did before, so minus 1 over 2 x squared plus 2 plus c, and that is our final answer. So now that we have done this case 4, you should be able to solve literally any partial fraction decomposition.